Okay, I think I'm going to get started today. See if we get some more people showing up as the class goes. I'm hitting record on this. We're going to do a unit 8 this week. Um, unit 8 is on uh, composite types and collections. So what are those exactly? So those are, I mean, it's kind of like data types that are made up of other data types. Like an array is a typical example of maybe a collection. It's an array of integers, so it's made up of a whole bunch of integers there. Um, Most collections like that are all made up of the same element, like an array of integers. Um, Composite types generally are like a group of types that aren't all the same, aren't all integers. We'll look at records. And so like a record would have like someone's last name as a string, someone's age as an integer, someone's date of birth as a date field maybe. So it would have, again, a list of elements, but again, they're not all integers. They're not all the same here. Um, so we're going to look at kind of those types here. We're going to do this again one more time where we have a bunch of AI prompts, and I've gone through and done the AI prompts, and then we'll just kind of walk through those today. And then after next week's spring break, of course. So after break, well, this week we'll ask and then we'll decide after break. I'm not quite sure what's the best way of doing this. If you prefer, if I just give you the prompts and copying the prompts and then AI and get the responses and read those. I like that because it's kind of more interactive on your part there. But again, I can also see the advantage of already having the prompts done because sometimes AI takes a while to generate them. So I'll send out another survey on Thursday asking sort of some feedback on which way we prefer this. But today we'll look at the prompts and some of the results of those prompts here. I'm just going to talk a little bit about the readings here. So most programming language textbooks have either a chapter on this or a section on this stuff. Current version of like Programming Language Pragmatics by Scott has a whole chapter on composite types here. I can't bring up a version of, I think we're on the 4th edition where chapter 8's there. I was able to just grab the 2nd edition here, and in this edition, he actually puts records and composite types in with the general type thing, chapter on types. But then he realizes in a later edition that this is a bigger topic and a more important topic, so he breaks it out into his own chapter. But a lot of this stuff is just taken and copied and pasted to the later edition. Again, some of this is good, but again, some of this is just a little old. I mean, so records, we'll start talking about records, and they come from COBOL and Pascal here. So he talks about quite a bit how Pascal does records and how you can do a record in C and how they're set up, and the memory layout of these things for this. The with statement here. So he talks about this sort of stuff in here. Variance in Ada for this. And then does kind of the similar thing with arrays. But I think he's missing a number of important topics here. I think a lot of this is out of date here. I don't know if you really need to know how Fortran implemented arrays for this. So we're going to look at this through a series of prompts. Let me bring those up here. Again, I'm going to just have these side by side here, and we'll talk about the responses, and we'll kind of compare ChatGPT with Gemini for this. So I think I'm going to maybe make this just a tad small, yeah. Let's do that. Okay. So records have been around for a long time. I mean, right away, and with some of the first programming languages like COBOL, that were that's what kind of set COBOL apart for doing business stuff is they had records there. And again, you could put a record on a punch card. So records are as old as paper punch cards, basically. Um, so again, early late 50s, early 60s, they were using these records. And again, it was just kind of like what you would think of a database nowadays, where you would define a record layout being a like the name of a customer and an order number or a age or date of birth, these different fields, and each field would have a different type for that. And you do it. And often, again, you might fit one of these on a punch card, and then you have a whole stack of punch cards to be a whole table of information, something like that. Pascal was popular in the 70s and 80s, and they really popularized records and using records then. Let's see what Gemini. So Gemini doesn't walk so much through the history of it, jumps right in C. So again, when C came out, it had a thing called a struct. And so again, sometimes records and structures are similar, idea, just different languages. So we have these structures. And again, here, character, a name, an age, and a GPA. So that's your structure here. And Gemini is doing similar stuff here in C, a struct with a book, a title, author, and a year for this. And then you could create a book, and set this. And again, this is looking to you. You probably think of this as an object here, but it's not an object in that it has no methods. It only has the data fields to it. We can still often use the dot notation. So we can say book one dot title here to go out to book and get the title with the dot notation. But again, here, let's look at some of the limitations of record, of structures, or that sort of stuff. So fields can be accessed and modified directly. There's no like getters or setters here. And there's no associated behavior, although when I learned to do structs and records, we are told to define the record and then define some functions on that. But again, they weren't explicitly tied together here. So again, no encapsulation, no abstraction, and no lack of behavior, no methods specifically tied to these. Then we transition to object-oriented programming here, the rise of the objects here. So again, we're talking is early 60s. We had some languages. Smalltalk was the 70s and 80s. No one really used that much. I mean, it was a nice research language and stuff, and people liked it. But again, until C grew into C++, we and added objects. That's when we really started to see object-oriented stuff. So we added classes and member functions. In the 90s, mid 90s, we had Java, and Java was made from the ground up. It was object-oriented from the start, building on encapsulation. So it was basically designed to be object-oriented and do all that stuff. So, and again, Python, all modern languages are kind of designed to be work with objects from the get-go often these days. So again, this is just showing you an example. So this is C++ here, where we have a student here. So this is just a structure, but we have a structure for a student. But inside that structure, we also now have a method display the student for this. So again, where in C, we could just have the member variables. Now we can have member variables and methods And again, you know how to do this in Java here for this. So again, we have another prompt asking that, to compare objects, records and objects here. And again, the old records only hold data, no built-in behaviors. And again, no getters or setters, no abstraction. You couldn't store things inside them one way and then represent them outside a different way or something like that. So no private and public kind of sort of stuff. So I'm going to skip over the rest of this. If you want to read more about objects, records and the history of that, that's fine. Now we're going to jump into arrays. I think you know normal arrays pretty well, so we're going to jump right into multidimensional arrays. I want to try to get into a lot of people ask, why is C or C++ so much, faster? Why do we still use it? And I believe a lot of it has to do with implements multidimensional arrays and works with multidimensional arrays. So that's what a lot of these prompts are kind of working towards, is trying to understand how, under the hood, how multidimensional arrays are done. And you'll be surprised they're done differently in different languages here. So again, we're thinking about a multidimensional array. And again, we're just starting with a two-dimensional array. But again, it should extrapolate to 3 or 4 or 10 dimensions easily here. So again, you're thinking rows and columns in a two-dimensional array. And then again, for this. So let's talk again. The way C and C++ handle multidimensional arrays are basically the same. We have the underlying stuff. So we'll be looking at C++ here. And they have what is called built-in support for multidimensional arrays. You can declare an array here, an array of integers matrix 3 by 3 for it. And again, same here. C++ has built-in support. Same matrix example, 3 by 3 is amazingly similar example of this. And again, to access it, we just say like matrix sub 1, sub 2 to access these components. Here we're using a double loop to print out the components of an array. That all should be kind of, you've seen all that before, I think, right? Now, Java looks similar, but it uses what is called an array of arrays. We don't have true multidimensional arrays in Java. We use an array of arrays here. And so the way we declare it seems similar, int bracket bracket matrix, and then we can declare that matrix here. Here's another example of Java. But we'll see that under the hood, these are going to be different in a couple things. So Python doesn't have built-in multidimensional arrays and doesn't have really multidimensional arrays anywhere until you start getting into libraries. And again, that's what a lot of Python has. You add libraries. So the common one is this NumPy library in like machine learning. We're always using NumPy as a library. So you just have to import it here, and then you can create an array. And again, this is going to be an array of arrays for this. Now, one thing to note with arrays of arrays is that in a lot of languages, you can actually have arrays of arrays, and the subarrays can be different sizes, maybe. They might not all be the same. They might actually not be a grid. It might be like a jagged array, sometimes we call this. So sometimes we see that with these arrays of arrays. TypeScript, similarly, no two-dimensional arrays or multi-dimensional arrays. We use arrays of arrays. And again, this looks surprisingly similar to everything else here. So again, true multidimensional arrays, C++, yes. Everything else uses arrays of arrays. Now, NumPy does have true multidimensional arrays built into like NumPy. So as an added library, we can do it. And we'll see that in this next thing. That's why a lot of numeric stuff with big tables and crunching numbers are done either with C++ or with Python NumPy because of these two yeses here. So we're going to talk about slicing and dicing. So you're envisioning, have you done the VR? What's the games where is it fruit coming at you and you're slicing it? What versions of those games have you played where you're slicing and dicing things flying at you? Have you played those? No Fruit Ninja competitors here. So that's disappointing. So, okay, that's what we're trying to do here is array slicing. So often, again, when we're working with a big array, how do we manage that? And you can ask yourself, why do we want to do this? And let's just talk a couple examples like graphics. So if we have the screen mapped out in memory, and then we want to get it and modify a certain part of the screen or move a sprite on the screen or change parts of it, we want to just grab a certain segment of the screen and modify that. And again, like a rectangle in a two-dimensional array for that. Or like when we're selecting data to do some manipulation, we might want to just grab, I need rows 47 through 50 or 55, and I need certain columns to do some sort of math, or I'm doing, applying some filter or doing some operation on this stuff. I often need to be able to quickly access parts of not just rows or columns, but often, again, a certain section, a subsection of this multidimensional array. So again, memory layout can really affect the speed that we're able to do this. And how we do this really depends on the memory stuff. Both of these are going to start with Python because Python's kind of today's most common, where you'll probably see it. I mean, this is where we see it a lot in machine learning. We define maybe an array, and then we can use this slicing to say, I want elements 1 through 4. So this is the notation. So we declare some array called R. So, and then we look at the array and bracket, and then we say 1:4 to grab items 1 through 4. So not the 0 row, but 1 through 4. And then this generally does not include 4. So this would generally include these 3 items in it. Again, it's going to return 20, 30, and 40 of this stuff. And again, they talk about just modifying a certain point of view here. And again, NumPy stores arrays in continuous blocks of memory. This lets us do this sort of stuff very fast for this. So TypeScript will allow you to do something similar in JavaScript, but it is going to be much slower. So JavaScript slice creates a new array and copies of it. So again, you can imagine if you have your screen and you're just going to grab some little section of it, we're going to copy that whole screen and then or grab that section. So we're not just going to grab a certain part of the memory or something. It requires a lot of full copies of that multidimensional array for this. So copying large arrays leads to large high memory overhead. So now let's talk about the old way. I really miss C and C++. I haven't programmed in those for years. I never really liked them, to tell you the truth, but I kind of still miss them. So, okay, C and C++, you can do something called pointer arithmetic. Again, pointers are just memory addresses, and again, we can since these are in contiguous memory, we can do pointer arithmetic. We can do some calculations and grab those memory locations for it. It's not like an array of arrays. Each subarray might be stored in a different location in memory, and then for that. But with C and C++, you're guaranteed that this whole 1 or 2 or 4-dimensional array is all stored in memory here. So you can, again, do pointers. You can set it. You can start with the array, the first element, and just calculate, say I want the first, the third or whatever element from that, and do array arithmetic there. So arrays are stored in contiguous memory, and you can do pointer arithmetic. There's no extra memory overhead for slicing via pointers. It doesn't create a copy or anything like that. Very cache friendly. Linear memory access improves performance here. So the way we lay this out is nice. So again, that's why you see a lot of low-level libraries written in C or C++, simply because if it has anything to do with multidimensional arrays, it's going to do it fast. Now, NumPy does this also in Python, and so that's why now you see a lot of work in machine learning using NumPy or a similar library, which again gives you direct memory access. Now, the next thing is kind of looking under the hoods. I was trying to decide if I should include this, and I thought some of you might just appreciate, by you wondering, well, what runs under the hood? What is an array here? So in most modern languages, there's what's called a dope vector for arrays. This is just kind of a description of what the array does. And again, sometimes it's just called an array descriptor here. So some languages store additional metadata for flexible indexing for this stuff. So again, dope vectors or descriptors. It's a data structure with metadata about an array here. So what does it allow you to do? It helps with boundary checking, dynamic arrays, like an array list sometimes, or a lot of languages now, the underlying thing is not what you would call an array, but like an array list. It's dynamic. You can add items to the array for this stuff. And we have type information. So our low-level languages don't do this. So like C and C++, they don't have a dope array. They just, when you declare array, they just give you that section of memory and no information is stored about it. And it's up to you to kind of manage that. You can get yourself in trouble. So C and C++ rely heavily on the programmer to manage the array and track the size and stuff like that. So Java, we're going to have, so we don't have contiguous memory. So we do always, every Java array is going to have a dope vector that's going to store the metadata about that for things like boundary checking and prevent out of bounds errors and stuff like that. So here's the Java thing, the base address where it's stored, the length, and then the type metadata. What is it an array of here? And it handles things like boundary checks. So JavaScript is very similar, TypeScript. So we have implicit descriptors or these dope arrays. So we keep track of things for every arrays here. And again, same sort of information for them stuff. So again, just under the hood, every time you declare an array, it's in modern languages that aren't C or C++, there's a little data structure that is declared a descriptor for that array or a dope message for that array. So have you seen much of this? Is this all, how familiar is this? So I assume that you've seen arrays. Are you familiar with these you've certainly heard the C and C++ are better. Did you understand? Does this help understand that much or? Yeah, a lot of it's like making tables and how you can slice and dice those. Did any of you do First Robotics? This weekend was a big First Robotics tournament down at the deck. So I was there Friday and Saturday all day. Hundreds of high school teams. Well, yeah, about over 100 high school teams there competing for First Robotics. It's always exciting. So, did any of you do First Robotics? No roboticists?
When I was really little, I did like,
Lego?
no, I did like a club.
Okay,
club
yeah,
in like elementary.
okay, cool.
Yeah.
So what kind of robots you build or did?
I forget what competition it was, but it was one of those where, you at the end of the year, you brought it to like a competition.
Okay.
You had to do certain tasks.
Yeah, yeah,
Bring clothes hangers from here to there,
okay.
that sort of thing.
Oh, interesting. Huh. Uh, okay, let's jump back into this stuff. So now we're going to look at just kind of some other generic or other collection types here and talk a little bit about a variety of different ones that kind of fall in these bands. So the first one we're going to talk about is strings here. Now, you might think of string as a base or primitive type, but really it's not in most languages here. So let's just talk about this. We're going to want to look at, is it mutable or immutable? Can you change, a string, or what happens when you modify a string? Do you make a copy of it internally? How is it stored there? And then encoding days, again, originally strings were stored in ASCII format there, but again, today, always we want to use some sort of Unicode support so we can support multiple languages and alphabets for these. So C and C++, they just declared a string as an array of characters here. Now, array doesn't have a variable length array, and strings are different lengths. So what they said was, okay, we're going to declare an array of strings of characters, but you can store things in your character, and then we'll put a null, a/0 as the end of the string. So that would mark the end of a string for this. So if you declared like here, character string bracket equals hello, that would store H, the character HELLO, and then the null character at the end for that. There, it's stored in contiguous memory. You could treat this as an array here, and that lets you do certain things. If you wrote it, if you could just like put the null different things. You could actually write functions. You could recover sections of text because again, I'm trying to remember what the maximum size. I think the maximum size of a string was like 255 characters. So they would give you an array of 255 characters, and then you would just you could put the null anywhere you wanted in there. But again, if you stored a sentence in there and later changed it and stored a shorter sentence, often the rest of the sentence was there just on the other side of the null. We could just move the null around sometimes for this. So we had these null terminated strings. They're just in memory. We could directly mutate them for it was just an array of characters here. So again, this is trying to show the memory addresses and how that works. It's just directly mapped. Now, in Java, it's totally different here. We use immutable strings. So once we declare a string, we're not going to change its memory there to change a string, like to add a character, like just to add an S to the end of a word there. we actually make a new copy of that string. So for it. So this like shows this example. I think both Chat GPT and Gemini use almost the exact same example. So we start with a string called hello. String one is hello here. And then we're going to add or concatenate the word world to that. Now this creates two different strings, shows it as two different strings. This uses the same variable again. And the idea is that if this is a mutable string, we would just add world onto hello, but that's not what happens here. What happens is that we start with hello in memory as a shared kind of variable for this. And then when we try to say add world to it, we make a whole new array, whole new string that says hello world and store that on here. So again, we don't change the underlying strings. We simply make copies of it. And again, you have to be aware of that when you're doing a lot of string manipulation and stuff like that. Now, you might not, for how often do you change someone's name in a database or something like that? You might not do it. But there are times when you're doing things when, sometimes like you'll be storing things in an array, like let's say you're just doing some DNA processing and all the DNA characters are storing in long strings there. And every time you want to manipulate or tweak one of those DNA strands, again, we're making a copy of that whole DNA strand just to tweak or change doing one simple mutation on it or something like that. So it is useful to be aware of this sort of stuff. And we'll see this in a number of other languages. So again, Python, strings are immutable, sequences of Unicode characters. Again, just like Java, all this is managed automatically. You don't have to worry about this stuff. And again, when we declare a string and add something, concatenate something to it, we make a whole new string. So we start with this internal string hello, and then we create a new string on the heap called hello world when we do this stuff. So similarly, TypeScript, basically the same sort of stuff here. So again, C, C++, mutable strings, we can change them. They're just arrays of characters. C++ did add Unicode support at some point. So we can have something that's not just ASCII. All the modern languages, again, or Java, Python, TypeScript, are not mutable. They're always taking copies of strings there. But everything is automatically stored in Unicode. So. Okay, so that's strings. Let's look at some of the other things. I thought we'd kind of group lists, sets, and bags together and kind of talk about those stuff. So, and again, what is a list versus a set versus a bag sort of idea. And again, you can kind of think of this like, let's look at math and a set in math. You can have a set of objects in math there. So, and each object is unique. So if you could talk about like the set of car types. So you could talk about, a Ford Focus or Subaru Outback there. So that's the set. But you don't, when you're talking about a set of objects and you say, I remember this Ford Focus is a car type. We should put that in the set, and you add it to the set. Well, if it's already in the set, adding it to the set doesn't add a second one. A set is each item is unique in that. It's just a list of car types. So thinking of and adding another car type to the list that's already in it doesn't really add it to the list. It just verifies it's in the list, kind of sort of idea. So again, we talk about like a set doesn't allow duplicates here. Lists do have. So if you have a list of car types and you think, Ford Focus, a Subaru Outback, What other, list some other ones. I think, oh, Ford Focus, you add it to your list. So like, my wife and I get this trouble all the time where I think of something to add. We have a shared grocery list, and I think of something to add to the grocery list while I'm in the kitchen. I add it to the grocery list. And so I'm not very good at looking at the grocery list to make sure it's not already on the grocery list. And so my wife just laughs because we'll be grocery shopping and, I've added something twice, she's added it once. And I've added it at least another time to the list there. So lists can have duplicates to them. So, now both lists and sets have generally can have an order. So that's the question is, do they? Now, generally in math, sets do not have an order. There's no order in a set there, where a list would have an order. Now, a bag doesn't have an order and does allow duplicates. So again, the whole idea is a bag is like this cloth bag where you're putting your marbles in it or your dice or something like that, and you can grab them out and that you always get a random one. You can't just say, give me the next. There isn't an idea of a next. You can just say, give me a idea. So let's look at this. What do we say? So again, lists ordered, duplicates allowed. Here, lists also called sequences. They're ordered collection of elements. They allow duplicate elements. We can access them by their position. We can say, give me the fourth item in the list. Examples are like arrays or linked lists or array lists, all that sort of stuff here for this. So again, Python has a list. Java has a list like an array list or a linked list. This is kind of a generic version. TypeScript has an array for these stuff. So again, we can directly access the elements in the list there. Finding and removing elements is slow with large lists because again, we often, sometimes we'll have to make copies of the list. There's an order to the list and stuff like that. Sets are duplicates are not allowed. Sometimes some places will maintain an order, but generally, the idea of a set is that they're not ordered here. So like Python has a set here and it's unordered. Java has these kind of hash sets or tree sets, and because they're hash, they kind of maintain some sort of order there. And TypeScript has a set again that just maintains the insertion order by default for this. Most languages don't have, or at least these languages, Python, Java, and TypeScript, don't have a built-in version of bags, which surprised me. I thought they would here. There are some things what are called multi-sets where you can implement these. But again, a bag is an unordered collection of elements. Here we allow duplicates here. Membership testing is efficient, and counting the number of items in the list is generally very efficient here. So again, we can talk about like a bag of marbles where we care about the quantity of each color of marbles, but we won't be asking to grab a particular marble often. So again, efficient frequency counting used for histogram style operations, word frequency, inventory counting, that sort of stuff. So we're getting into this O notation. So have you guys had big O notation? So if we have like big, O notation for its log n order. So you do that in data structures. You do that in Java too, you remember?
I don't think we did it in Java too.
Okay, but data structures, you certainly talked about it. So again, that's big O notation just is approximately how long does it take to do something here. How many operations? So big O of 1 just means that it'll just take one operation. We can have a single command to go out and do it here. Big O of n here, so like a searching through a list might be big O of n. Let's see what's yeah, finding or removing elements in the list. Oh, you probably, assuming it's a non-ordered list, you're going to have to go through and look at each item in the list. It could take, you might have to look at all the items in the list. So that's big O N here. But for lists. But again, they're saying one thing that's nice about these bags is that things like lookups are off. It could be order log n, particularly if we're using trees to store this data. I'm gonna go down here and talk. There's another thing that talks more about the differences here. I'm gonna skip that and jump to maps here. Maps, dictionaries, lookup tables, associative arrays, they're all kind of the same thing. I don't think we spend enough time teaching how to use maps and things like that as we should in these classes, because I think in the real world, these are actually used an awful lot here. So again, we're looking at these key value pairs, storing things in. And again, sometimes they're called associative arrays because they're like arrays, but rather than specifying that I want element 47 in the array, you can say I want the customer Gibbons, or with you specify a last name or something like that, and you'll get that customer based on some key. You specify some key to look up in the data structure, and it will return some value there. So keys are generally unique and map to values. Values can be duplicated, so you can store the same thing multiple times, but each key should be unique here. And again, they should offer very fast lookups, unlike lists where you might have to store these. So again, Java uses a hash map or a tree map for storing these. So a hash map is basically just a hash table. To look up an item is a single, we just calculate a hash to find that item in memory. So it's just a quick linear, single operation to look up things. Tree maps are slower, but they maintain an order. So hash maps are unordered. If you want to maintain a sorted order, you can use tree maps for this. I was thinking, have you covered hash maps and tree maps? Do you cover those in data structures? I was right. Good, because I wasn't going to do much about them, assuming that Chris covers them. And again, so they just go through the simple example here where you're creating a hash map with a string and an integer. We're storing Alice and her age and Bob and that sort of stuff. And then we can just get Alice's age easy enough for this. And again, that's really fast lookup for large things. And again, we run into problems with collisions and stuff like that. Python will have this dictionary. And it's again basically a hash table. You can specify this table where you specify key value pairs, similar stuff, fast order. It does maintain the insertion order for this stuff. We should talk when we talk about order. What I think about there is, can we iterate over that? Is there a next operation there? So in most of these collections and stuff, like an array, we can always ask, given some element, what is the next element in it? So again, if we're storing this as a linked list or an array list or array, there's always some way to ask what's the next element in that collection. So again, often when I see this maintains insertion order, to me that means that we can ask for the next element, and that means we can do like a for each over it. Often we can loop over and do something with each element in that dictionary. Where often with some trees and stuff, there might not be a clear way. So again, this is our dictionary. It's a hash table. Big O of 1 here. Good average performance. Insertion orders preserved starting in 3.7 version of Python. So TypeScript as a map function or data structure. So again, map of strings and numbers. And again, you set them up and then you can get those, and it's an order 1 lookup. One of the goals of this course is to, and one of the reasons why we look at this in multiple languages is to kind of try to see the underlying unifying theory behind these data structures so that you don't just think of it as something you can do in Java. You think of it as an abstract thing. There's a kind of this map concept. Different, it's interesting because people who know this often will refer to it as different things. So, you'll talk to other developers and they'll call it, a dictionary, or they'll call it a map, or they'll call it an associative array, just depending on how they were taught. But they're all the same thing. And again, depending on the language, all of these, the implementation of these are all very similar. So again, we're calling it a sort of a dictionary, dict here, or a map here, like a tree map or a hash map here, or we're calling it just a map here. But they're all very similar sort of concept. So you should just be aware, when would you use a map and why would you use a map for things here. So again, here's this kind of a quick comparison of them. And again, most of these are implemented with either a hash table or some sort of a tree implementation for these. So let's see. So I didn't expect AI to do this sort of comparison on this original prompt. So then I asked it to do that. And so it basically does the same thing again here. When to use a list, when to use a set. Well, I guess this is different languages. Here we're asking, when should you use a list? When should you use a set? When should you use a map for things? And how they're implemented. So again, lists are like array lists or linked lists. In Python, they're just arrays, and TypeScript, they're just, lists, and in TypeScript, they're just arrays here. And sets, we have hash or tree sets or just sets here. And maps, we have hash maps or tree maps, dictionaries or maps for these. So, and again, one of the questions is do you want duplicates? So the only reason generally you use a set is if you don't want duplicates, and sometimes that helps with your stuff to not have duplicates automatically. And then the lists and maps, how quickly do you want to sort through them here? So this is talking about lists, and again, access can be order 1 just to grab a single element here, or with linked lists, it can be order n. Insertion or deletion here, depending on if you're adding the beginning or the end of the list, it can be order 1. Otherwise, you may have to, if you're adding in the middle of the list, you might have to shift every element down. So again, depending on how the list is structured, inserting in the list might take a while. And again, searching is order n for this stuff. And where dictionaries, again, often to find the element in the list is order 1. Inserting, deletion, searching, all are generally very fast for these. Okay, I'm gonna scroll over some of this stuff. Um, and again, here's a good table kind of showing lists, sets, maps, tree-based sets, and tree-based maps here, and inserting, deleting, and searching what order of operate, how long is this going to take? So, I sent out an email with some more jobs that are being posted out there. There's a couple in Superior and Duluth. There are a couple down in the Twin Cities. So again, if you're still looking for a job, if you are graduating in May and looking for a full-time position, let me know. And I haven't been posting too many of those. I don't know. So just send me a quick email reminding me that and remind me where you're looking, and I can start adding more full-time jobs or entry-level jobs for May grads for that. So, okay, we're doing all these just kind of miscellaneous today steps. I thought I wanted to cover data frames and Pythons and talk about tabular collections here because again, that's kind of what an array is, but some languages will have a special kind of structure for that. And again, in Python, it's generally called a data frame. So again, a two-dimensional tabular structure here. This has been around for a long time, basically. I mean, back when we had COBOL and Pascal, we would declare records and then we'd have an array of records. So again, probably the most common data structure out there was an array of records. Again, that was basically a two-dimensional table. Each column was some different field in the record, and then each row was an array. You know, we had an array of elements with entries, a separate record in that table. With these, we have rows and columns indexing heterogeneous data types. Each column can have a different type. So it's not necessarily an array where an array of integers here. It would be like an array of objects sort of stuff, your array of records. So not everything's not homogeneous. We have this heterogeneous idea. So we also often have some very fast math on these because again, the Python NumPy is storing these in contiguous memory, so we can do what is called vectorized operations. We can use our GPU to do very fast calculations on this sort of stuff. But again, this is talking about the same thing: table structured, label accesses, heterogeneous data, efficient operations for like filtering, sorting, transforming the data here. So, and again, in Python, we have this NumPy. We can just declare an array data frame. Panda has a data frame type object. Now, in other languages, we have to bring in an external library. So Java has a library called Spark we can bring in, and we can have what is called a data set and declare that and work with that here. So both of these are talking about Apache Spark for Java. And again, with TypeScript, doesn't have built-in support, but again, you can bring in this library and work with data frames. So. No, these aren't all as fast here. So like Pandas is optimized for very fast performance here. Some of these have longer performance and some of them are better. So you can kind of look at what you need to do and try these out. So. I thought we should just talk about trees and recursive, what are called recursive data types, pointers. You do this in data structures, so we'll do this relatively briefly there. So again, if you're going to build a data structure where you have an object that points to that object of that same type, that's kind of this recursive data types. here. C and C++ have built-in low-level support for these pointers, but all modern languages like Python, Java, TypeScript will have this through objects here. So, and again, you've created these in data structures, linked lists, trees, graphs, any sort of these sort of connected data structures you can build with this stuff. So again, I'm not going to go through these examples. Again, if you want, I mean, if you haven't seen these before, this is good, but I think all this stuff should be just stuff that you had in data structures here. It is, you do data structures in Java, right? You did that in Java? Yeah, right, the data, when you did linked lists and stuff. So I get, what? Yeah. So you can do, I mean, you can just as easy, it might be, it's sometimes nice just to look at how it's done in Python and stuff like that. So you can do this stuff. You can create a linked list in Python here, declare a tree node here, and it has a left and right pointers to the tree here. And you can set up a tree node and then set up the left and right pointers to other tree nodes for this. You can do the same thing in TypeScript here for this. So again, none of these have explicit pointers. They all use these references. None of these, you don't have to worry about garbage collection on any of these. They all have automatic garbage collection and stuff like that. So makes life pretty easy. I mean, again, this is stuff I think you've seen before, but get what are the different types of trees out there? They talk about just a generic tree, hierarchical structure for this, binary trees, binary search trees, balanced trees like red-black trees here, heaps. Now, when we're talking trees, heap is a specific, it's not the generic concept of a heap from memory. It is basically kind of a priority queue where it's an ordered list or, you know, things so we can quickly find the largest or smallest item depending on how we're sorting it here. And then B trees. So again, I'm not going to go over these because I assume you've seen these in data structures courses. So. Now this is where I wanted to talk more about, and this is where I didn't think the textbooks really covered anything. I want to talk about generic interfaces to types. Because I think once you get into real production-like level code, you're not actually going to be working with array lists or stuff. You'll be working with some higher level interface type of this. So let's talk about that. I'm going to talk about it in C+, C# first, because that's probably where you've seen, if you've had like, I'm thinking of our software design class or our game design class, both of them we get into this stuff. So there are types like IEnumerable here, which is just any sequence of objects that we can iterate over. Some other languages, this is called IIterable or stuff. So it's a base collection, and all it has to have is a next operation. So as long as we can ask what's the next thing, and we can, so it basically IIterable is anything we can do like a for each kind of loop over it, where we can loop and guarantee this loop will cover every element in the list or whatever the underlying collection is. So. There's iCollection, iList, iDictionary, iRead-only list, iRead-only dictionary for this. So iCollection extends IEnumerable here. We add some new features like add, remove, and contains. So we can search, we can add and remove things. to the list here. So if you want to do more than just loop through it, there you can use iCollection for this. And then iList extends iCollection, provides some more things here. So again, accessing direct elements. So IEnumerable, you can't access direct elements. iList, you can. So I say, give me the 45th element in the list here. So again, often when you're coding or you're writing a passing data structures around, you're going to say, how much do I want? Do I need a list with where I have direct access to the things? Can I get by with a collection? Can I get back by with an enumerable objects here? So that's in C#. Java, again, we have iterable, collection, and list. Again, these are generic. So iterable is similar to IEnumerable, collection is similar to iCollection, and list is similar to iList. And again, we have maps and sets also there, these generic types. And again, you've probably seen this even when you've declared like an array list, you probably stored it as a list object for this. Yeah, so there's our versions of those. Python. We have iterable sequence, mutable sequence mapping, and mutable mappings for this in Python. Again, we have to bring in some explicit typing here, because we don't generically type, do a lot of type enforcement in Python. So again, you've got to kind of tweak these to have this in Python. TypeScript, let's see, oops, this is that. Okay, this one has TypeScript array, set, and class here. I mean, array, set, and map are the TypeScript equivalents on this. One thing you'll see, like in what I call the scripting languages, the JavaScripts and the Pythons, they don't have a basic array like Java has a low-level array here. So what they have when they say array is really an array list. So in like JavaScript or TypeScript or Python, when you talk about an array, it's really an array list. It has additional function. It is, you know, under the hood, it's implemented probably with like a linked list or something like that, right? You can add elements, you can insert elements, you can change the size, all that stuff that you would, you know, what you think you can do to an array list. In these other languages, they're just calling it an array here. So like, you know, TypeScript, an array is just an ordered collection here. Now, why do you do this sort of stuff here? The main thing is abstraction and flexibility. You want to decouple your implementation details of the collection from the code that uses it. So you might start by using an underlying array list there, but later on you say, oh, this would be faster if I used a map or a tree of some sort. But again, if you are returning it as a generic type, all the software that uses your class doesn't have to worry about that. So again, here's walking through using IEnumerable rather than a list here. So here's the bad way. We use list directly. Here we have a method called print names that we give it a list of names and it prints it out. And here we create a list of names and we call print names for it. But it only accepts a list of names. We may want to change this to like a hash set or a queue or something like that here. And then, so if we were to change this names to be a hash set, now we couldn't do this. A better way, of course, is to declare our method here to use an IEnumerable of strings here. Again, and we know we're just implementing it in this one function. All we need to do is a for each. So we don't even need an I collection or an I list. We just need an I enumerable. We just need to be able to do a for each over this stuff. So we can declare this as the most kind of generic type, an I enumerable. And then again, if we have a list or a hash set, either of those we can call and pass to this function. And again, we talked about this in software design some, but again, that's what we're doing. And I thought we should bring it up here because again, we're talking about all these data types. And again, these are kind of the high level wrappers that go around these sorts of data types for things. Okay. Now the last two prompts I give are just trying to ask for best practices on all this stuff. And I wanted to see what AI kind of came up with. It did okay. So again, compare and contrast all these, implement composite or types, discuss design trade-offs for these. So again, this ChatGPT created a nice chart here, Java, Python, and TypeScript. Talked about lists, ordered, mutable, list, ordered, immutable, sets, maps, queues, and trees. And, can you do these in these languages? And one thing I didn't mention was tuples. I almost included those, but to me, only place that we use tuples are really in like game design where you have these coordinates, X, Y, Z sort of stuff. So a tuple is like a fixed number of elements here. So if you're interested in tuples, you should do some more work. I think that this one actually has a whole little section on tuples here. But again, they're not built into Java. They're not built into JavaScript, TypeScript, but they are in Python, of course. Okay, so again, this tries to walk through the same thing, collections, and talks about each language. Here has this nice feature of each language. How is it typed? What kind of composite types does it have? What kind of collections does it have? Performance. Here, syntax, and that's just, I don't know. I didn't find that all that useful. Here. I'm going to go on to the next thing. Well, this one, I thought this wasn't a bad thing. It's talking about the design trade-offs of these languages as far as type, safety, or performance here. Now, this is talking about performance, and say Python is slower because it interpreted. And I agree. But again, there are some libraries in Python like NumPys, which are very fast and faster than often Java or something like that could be. So depending on what you're doing, you can get better performance here. Okay, last thing is just some best practices, what you should be doing here. One thing I liked just was listing common kind of pitfalls in different languages. And again, these are things I think we're aware of. So most of these. So again, the mistake of using equal equals instead of dot equals for comparisons. There. Using hash maps and not considering a collision with them here. So they talk about Python, some mistakes. Using lists for something where you have frequent insertions and removals there. Again, in lists in Python, very slow to add or remove items out there. There are better types for that. Using mutable arguments by default as the default arguments here. So again, sometimes if we're using an array or a string, again, and passing it in, we're making more copies than we need to for some of this stuff. So, this talks about, not using maps like you should, using kind of a generic array of types here when you really should be using an actual map in this is in TypeScript for this stuff. So again, you could read through that and see some of the suggestions in these different languages. But again, I didn't think it was that great of a response that either one of these gave for this. Again, so remember, generate a question, a quote, and a talking point for this. I mean, not talking point, your own student prompt. So after learning this, what are you curious on? What prompts do you want to try out and generate those and post those to the discussion area by Thursday's class. And we'll do that for discussion on Thursday. We're going to do a learning activity. I haven't finalized it yet. We'll do this on Thursday. There was a podcast, and they always had a segment called Yes, Yes, No, where they would talk about something and someone would know it, so someone wouldn't know it. And so the other two would know it. The two yeses would try to explain it to the person there. I want to do something similar. We're going to look at some of these data structures and we're going to look at two bad ways to implement it and one good way. So we're going to look at a problem and then have you implement it in two wrong ways and then implement it in a better way. So that's our goal. So I'll have a set of problems and we'll talk about what data structure, what collection should you be using, and what's kind of interesting is a lot of these you could use and a number of these different collections or composite types. So the question comes up is, well, if you can do it in any ways, is one better than the other? And often there is. So that's what we'll try to do. So we'll do that on Thursday for this. And then I'll have a short assignment also set up. I'll try to get those done tomorrow, so they'll be posted. Questions on this? No? Sounds good. All right, we'll see you on Thursday.